For this video, I want to talk about a brief introduction to special relativity, and then we'll do worked problems in a later video. So this is on page 57 in volume 5, and there's going to be a lot of terms here, so you might just kind of, and all of this stuff is already written on page 57, but hopefully by listening to me, maybe then when you read this page, it'll make more sense. Let's get into it. There's a thing that these are some terms we're going to use. Reference frame. I want you to think of a reference frame as basically a coordinate system. Here we see two coordinate systems. There's reference frame S, that's this blue one here with the solid line, and then there's frame S prime, which is moving to the right with some speed V. That's the dotted red line there. Okay, so a reference frame is a coordinate system. Great. What is an inertial reference frame? That's a frame that moves with constant velocity, not necessarily constant speed. We have to have no acceleration. So if you have constant speed and your frame was moving in a circle, that is not an inertial reference frame. However, if you have constant velocity, basically straight line, constant speed, you have no acceleration, that is called an inertial reference frame. Lastly, we're going to see this term event. That's something that occurs at a time and a place. So I want you to think of an event here. There could be some time that this happened at some x and y. Now, a person in frame S would record the event as having coordinates x, y, and t. The person in this other frame would have possibly a different value of x, so we'll call that x prime, and possibly a different value of y, y prime, and maybe even a different value of time, t prime. Okay, so basically, you can think about adding time to your coordinates. So there's x, y, z, that's the location or the place, the position, and then there's also time. Those four coordinates determine an event. Okay, so now this is going to get pretty wild. Okay, hang on. Postulates of special relativity. So you sometimes hear me say special rel, just because I'm lazy. Okay, but some postulates of special rel or special relativity. Number one, the laws of physics are the same in all inertial reference frames, and the speed of light in a vacuum, basically this is the parameter c, is also the same in all inertial reference frames. All right? Now, there's more consequences than what I have here, but in order to get this done, I just kind of want to give you some of the weirdest upfront things that immediately become really uncomfortable. Okay, number one, simultaneity is not absolute. This is so weird. I could view two events as being simultaneous. You could view them, if you're moving really fast, as not being simultaneous. And we would both be correct. What? More on that later. Okay, it's very difficult to accept that. But basically, I could see two light bulbs flash at the same time. You could see one of them flash first, and we would both, and that's assuming we calculate the times for light to travel and everything. More on that later. It's just really uncomfortable. Simultaneity is not absolute, right? One person might see two events happening at the same time. A different person would not. That's a fact. Number two, a clock that moves along with an object records the proper time. Clocks that are moving relative to that object run slower. They record longer delta t's. So we'll use this phrase proper time. And different books will use delta t 0. Some books will use tau. But I want you to think about this. I'm in a reference frame right now, right? So I'm just going to start walking. You can imagine I'm timing something here, right? And so I'm timing maybe how long it takes for me to take 3 breaths or something, or 10 steps. So I could record a time, and then obviously I'm measuring the time in a frame that is at rest relative to myself. I am not moving relative to myself. I'm always moving along with myself. So I would be able to record a proper time for events like my own, how long it takes me to breathe. Whereas someone that's moving parallel to me at a different rate would record a different time, right? So that's very unusual. Okay, and so they would record more time for those events to happen. Great. Next, An observer who is at rest relative to an object measures its proper length. Let me just get this here. So right now, I'm at rest relative to this meter stick. So I would actually measure the proper length of this meter stick. But if I was moving relative to this meter stick, I don't know if it's gonna, oh, I forgot that, okay. But you could just imagine if I was running this way, so if I was running past this meter stick this way, I would not measure the same length. And we would both be right. The person who's at rest measuring the meter stick would get one length, that's called the proper length. Right? When you're at rest relative to the object, you record the proper length. Anybody else records a shorter length. The length contracts. All right, so those are very unusual. Now we've got some equations to make sense of this over here. Let me keep going to this board. Those are wild consequences. We're going to see this thing beta all the time. I want you to think about beta as a speed, right? It's speed in units of c. So if you just multiply this, notice that v equals beta c. If you check, this has no units. But essentially, if you tell me what beta is, I'd be like, oh, multiply beta by c and I'll get the velocity. So that's what I mean by beta is essentially the speed in units of c. So if it was, for example, 0.93, that's 93% the speed of light. If beta equals 0.93, for example. Okay, so that's a speed effectively. This thing here is called gamma, the Lorentz factor. All right, it's related to beta. Great. And it turns out if we see time dilation, this is what I was just talking about, one of the consequences, the proper time, delta t0, is recorded when both events occur at the same location in space. So if I'm sitting here and I'm recording times and the events are happening right here at the same spot, I will record the proper time. Whereas if I'm moving by as the events happen right here, I would get a different time. And gamma, as it turns out, will always be greater than 1. Take a look, right? It's 1 divided by 1 minus a little bit. So this is always going to be bigger than 1. So notice these other times measured by other people in other frames will be longer. All right. Now, length contraction has the opposite form. The person that measures the meter stick at rest records the proper length, L0, and so you divide by gamma, you're dividing by a number that's bigger than 1, that length will decrease. So we call this length contraction, time dilation, right? If you're measuring the proper time, everybody else records a longer time, it gets dilated. If you're measuring the proper length, everybody else measures a shorter length, lengths get contracted. Cool. And we'll do some practice problems. This is very confusing to try and read the words in the problem and identify. So identifying the proper time and proper length frames is a critical part. We'll practice that later. But just for now, I was curious about this question, and then I'll end with the importance of this. So what value of beta gives a 1% relativistic correction? I think this is worth doing really quickly. So let's just solve for this, right? So 1.01 is equal to, we could square this, right, to get rid of the square root. And then I could what? Cross multiply, and actually I'm just going to flip these, right? 1 minus beta squared is equal to 1 over 1.01 quantity squared. And then I could switch this around. What do you get? Beta equals, let's get beta squared equals 1 minus 1 over 1.01 squared. Oops, it's beta squared. So beta is equal to the square root of 1 minus 1 over gamma squared. I guess I could have written it that way and just left it as gamma. Sorry about that. Gamma is 1.01. Let's quickly do the math on this one, right? And so you should practice this, right? We're going to be using this a lot. So you might as well get used to doing the math now. So 1 divided by 1.01 x squared. 1 minus that. And then what? Square root that? And I'm in scientific. Let me get out of there. And then I need to square root that. All right, I better start over. So 1 divided by 1.01 x squared, 1 minus answer, square root of answer. There we go. So I got 0.14. What else? 1404. Now look at this. What does this mean? I've been talking about special relativity and these weird consequences. What we're seeing is you'll only notice a 1% difference in the length or time if you're going 14% the speed of light. That's pretty fast. So this is why this seems preposterous to us in the real world, because we're like, well, nobody's ever really going that fast. But it turns out satellites in orbit are going fast enough where if you want your GPS satellites to work, we need to take this into account. And general relativity too, but that's beyond the subject of this course. But so we'll kind of keep an eye on this, and for a lot of problems, we'll try to ignore special relativity if our speeds are less than about 10% the speed of light. Because unless you're exceeding 10% the speed of light, this correction and any corrections we'd probably see is pretty darn negligible. All right, so just be aware of that. That's all I wanted to bring up with that. And I wanted to end with a few things about the importance of this, right? And so, got that over here somewhere. All right, so let's take a look at this. Why is this important? Let's summarize. The laws of physics are the same for different choices of coordinate systems, okay? High velocity particle physics is now going to be accurately modeled if we use this information. Without it, we can't even understand an electron moving in a straight line interacting with a photon or something, right, if the speeds are high enough. Objects with mass have a speed limit. This is a big deal, right? So maybe this is probably the one that you'll be most interested to learn. Later on, we'll see that the kinetic energy goes to infinity if you have a particle with speed c, which is impossible. It would take infinite energy to speed up a particle such that it's going the speed of light. Said another way, any object with mass must be going slower than the speed of light. Otherwise, it would have infinite energy. Impossible. Okay? It's required for a complete understanding of electricity and magnetism. Great. Space and time are entangled. This is a bit like what we were just talking about. The time between events is affected by the distance between them. And similarly, the distance between events is affected by the time between them. Really tricky. And lastly, I already kind of mentioned this. If we don't use special relativity in our models, GPS systems would rapidly become inaccurate and unusable. So there's some practical things. We'll get into work problems in a minute, in the next video.